We've already learned that an electric field or an electric charge, I'm sorry, can be positive or negative, and that when an object has a positive or negative electric charge, it has a field around it. And because of this field around it, forces can be exerted from a distance. So how do we model and measure the strength of electric fields? In this case, we have two charged balls hanging from insulating strings, and we put a charged cube in between them, a positively charged cube. We know that a charged object can attract or repel a second charged object. We've already learned that opposites attract and like charges repel. So this depends on whether the object's charge is like or unlike the first. In this case, we see that the positive ball is repelled by the positive cube, and the negative ball is attracted to the negative cube. Sorry, I didn't have the window quite at the right size, but here it is. It should be a little easier to see now. The the force that attracts the positive ball toward the I'm sorry that attracts the negative ball toward the positive cube, that's called an attractive force. Okay, it's attracted to it, so there is a force attracting this ball into this cube. So you could draw a force vector to show that. There's a repulsive force between the positive cube and the positive ball, so you can draw a force vector to show that. And you could also show the forces on the cube, because remember, every action has an equal and opposite reaction. So if the cube pushes or pulls on the ball, then the ball pulls or pushes on the cube with the same amount of force. So which sphere in this case has a greater magnitude of charge? How can we tell? Well, we can look at the angles they're forming, right? The string on the positive ball is at the same angle as the string on the negative ball. So they're both being pulled with the same amount of force, right? If there was a stronger force pushing the positive ball away, we would see that this angle of the string would become smaller. It would be pushed farther. So in this case, the angle is the same, so they both have the same amount of force acting on them, but they're different distances from the cube. So since the cube is closer to the positive ball and farther from the negative ball, we can infer that the negative ball has a greater charge, because we're getting the same force from a longer distance, right? Longer distance. Okay, so the sphere that has the greater magnitude of charge must be the negative sphere. What would you measure to compare the amounts of charge on the spheres? Well, we could measure the distance, and we could compare the charge of one sphere to another. If we get just like in this example, if we get the same angle of the string, so we know that the same force is the same lateral force side to side is being applied to each of the balls, then we could say, okay, whichever one is farther away has a greater charge on it. We can't measure like in terms of numbers, but we can compare. Charged objects are surrounded by electric fields. Anytime an object has a net positive or negative charge, it is surrounded by an electric field. An electric field is the space around the object in which a test charge would be affected by the electric force. That means if you put um, a charged particle with no mass. So if you just took a charged particle, an imaginary charged particle, and put it in a region of space, and it was either attracted to or repelled by the object under study, then that would mean that the test charge is in that object's electric field, if it's attracted or repelled. Now, test charges are typically, the standard test charge is a positive charge, which we'll see why that's important in a moment. If you take a test charge, not a test charge, if you take a point charge, so here we have a charged object, this metal piece is charged on the tip. If we take this and we call that a point charge, and we take a bunch of grass seeds and scatter them around that point charge. Grass seeds are very, very small. We see a pattern where the grass seeds scatter, they come together and they form they form lines radiating from that point charge. So they're affected by that charge. They are in the electric field. These lines show that there is an electric field around that point charge. Where else could you see this kind of pattern? Well, if you take a magnet and scatter iron filings around it, iron filings are tiny little pieces of iron, just like the grass seeds are tiny little particles or pieces of, they're tiny little objects. So if you take iron filings and scatter them around a bar magnet, remember a bar magnet has a north pole and a south pole, we see a very similar pattern around each pole. So the iron filings form a similar pattern, but they're doing it around each pole. We draw lines like these particles draw lines. We draw lines to represent an electric field. And we draw the lines the lines have direction. So that we draw them like arrows pointing toward or away from the charged object. How do you know if it points toward or away from? Well, they point in the direction where if you took a positive test charge and put it in that electric field, which way would it move? Which way would the force be acting on it? So if you take a positive test charge and put it near a positively charged object, it's going to have a force pushing it away. So we draw arrows pointing away from the positive charge. If you took a positive test charge and put it in the electric field around a negative object, it would be attracted to that negative object. And so we draw the field lines with arrows pointing toward the negative object. So what if you took a positive object and a negative charge object and you put them next to each other? What would the field lines look like? Here we have a positive and negative, positively charged object and negatively charged object. So if we want to draw the field lines to show the electric field, and this is a model, you can't actually see field lines unless you put a charged object in it, like iron filings or grass seeds. I'm sorry, not iron filings. Grass seeds. Iron filings do not actually, they react to a magnetic field. Grass seeds react to an electrostatic field or an electric field. So lines should exit. So if we took a positively charged test charge, a positive test charge, and put it in space here, it would be repelled by the positive charge. But once it got to here, it would be attracted to the negative charge. So we can draw a field line like that shows what happens when these two fields overlap, right? So you have an overlapping field. So the positively charged object has its electric field, and the negatively charged object has its electric field, and they overlap, and so it becomes one big region of space. So if you put a test charge in that region of space, it would follow a pattern. It would go something like this. And so we draw, and of course my drawing's not perfect, but And then once you get far enough away, okay, actually let's go all the way to the end. Okay, your magnetic field lines would go more like that. And you would have the same phenomenon, um, the same model on the negative. Oops. Okay, I guess my. All right, so we would have, if we put a positive test charge there. Oops, wrong way. Well, I think you see the pattern. Oh, that's not even close to being a good one. Okay, I want to draw the same number of field lines because I want to show maybe this one should curve more this way, and this one more up there. So if you put a positive test charge anywhere in this space around these positive and negative charges, they would move toward the negatively charged object and away from the positively charged object. And that is pretty similar to what you see, to what you see here, right, with the magnet. You see that these iron filings, because you have north pole and south pole of the magnet, so they form field lines that are really similar to what I attempted to draw. Okay, let's look at if we put two unlike charges together. That's what I just drew, a positive and negative charge. But what if you had a positive and a positive charge together? Well, that's what we see here on the right. So we see that if we took a positive and positive charge and put them together, then we see that if we put a positive test charge in there, then it would repel from all of them. Okay, it would just both charges are repulsive. And if we had negatively charged objects, then the field lines would point toward the object. It looks like on the right side, it looks like there are more lines, but there aren't. Go ahead and count them. It's the same number of lines. They're just because they are radiating, or because they can't fill that space in between the two particles. We see that they get kind of smushed together. Okay, and the closeness of those lines represents the field strength. All right, so if we drew vectors, okay, vectors don't follow. Vectors only go in straight lines. Remember, they don't follow curves. So these field lines are not vectors. Don't mistake them for vectors just because they have arrowheads on them. But if we took this, if we wanted to draw force vectors on these test charges, A, B, and C, well, with A, the force vector would be kind of that way, right? So where the field lines are pointing at that point, that's the direction that the force vector will point in a straight line. Now B, what kind of force vector is on B? B is just trapped there, right? It probably wouldn't stay there for very long because any kind of movement would have it launch up this way or this way, or straight, straight, there, straight. But those are not actual force vectors because it's being basically the forces on the B particle are their B point charge. It's not a particle. The B point charge are balanced right now. Okay, because it's being pushed from the left, pushed from the right, balanced. And for C, its force vector would be out in this direction. And get used to seeing these force these field lines, because the field lines are how we represent forces. This is a model, okay, this drawing. So the picture on the left is a picture, it's a photograph. This is a real life phenomenon. And the drawing on the right is a model that describes or explains the the phenomenon that we observe on the left. So this is a type of modeling, and we're going to use this model, these field line models, to explain what happens in various phenomena.